All right, welcome back. And so now we're going to start section 1.5 on the shortest path algorithm. When you visit a website like Google Maps or use your smartphone, you ask for directions from home to your aunt's house in Pasadena. You are usually looking for the shortest path between two locations. These computer applications use representations of the street maps as graphs, with estimated driving times as edge weights. Moreover, they use an algorithm called it's called Dijkstra. Dijkstra's algorithm. The pronunciation's there. To find the shortest path between two vertices. So here's how Dijkstra's algorithm works. 1. Mark the ending vertex with a distance of 0. Designate this vertex as what we call current. 2. Find all vertices leading to the current vertex. Calculate their distances to the end. Since we already know the distance the current vertex is from the end, this will just require adding the most recent edge. Don't record this distance if it is longer than a previously recorded distance. So that's step 2. Step 3, mark the current vertex as visited. We will never look at this vertex again. And then step 4, mark the vertex with the smallest distance as current and repeat from step 2. Okay, so let's do an example. So in example 22, suppose you need to travel from Tacoma, Washington, vertex T, to Yakima, Washington, vertex Y. Looking at a map, it looks like driving through Auburn, then Mount Rainier might be shortest, but it's not totally clear since the road is probably slower than taking the major highway through North Bend. A graph with travel times in minutes is shown below. An alternate route through Eatonville and Packwood is also shown. Okay, so what we're going to do is step 1. Our ending point is Yakima. Okay, and that's going to be a distance of 0. So here's our ending point in Y, right? So we see we have that marked as a distance 0 from itself. That's where we're heading. Okay, and then we record all the distances from that point or in between points, right? So we've got all the distances between the different cities marked on the graph. Okay, so now what we're going to do is we're going to take all of the distances of the cities that are connected to Y. Okay, so what we're going to do is just illustrate. Okay, so step 2, for each vertex leading to Y, we calculate the distance to the end. And so those are in brackets. Okay, so obviously North Bend is 104 miles. So we've got that in brackets here. And we've got 96 in brackets here. And for Mount Rainier, and then we've got 76 for P. Okay, now step 2 says for each vertex leading to Y, calculate the distance to the end. And we've got the example, for example, NB is a distance of 4, so we have that in brackets. MR is 96, and so and P is 76. Okay, remember that distances in this case refer to the travel time in minutes. Okay, yeah, I think I said miles. These are not distances. This is the time in minutes. Sorry about that. Now, steps 3 and 4 says we mark Y as visited, right? So we're never going to go back to that. And then mark the vertex with the smallest recorded distance as current. So of these three times, 76 is the lowest, right? And so at this point, it's going to be P. So P is going to be marked as current. Okay? So now we go back to step 2. Now what we do is we say for each vertex leading to P and not leading to a visited vertex. Right? So Y is what we can't go back to Y, right? So we don't care about Y, but all of the other vertices. Okay, and we find the distance from the end. Okay, since E is 96 minutes from P, and we've already located P, calculated P is 76 minutes from Y, we can compute E is going to be what? 96 plus 72. So we add the path, right? Okay. So that gives us 172. So that's what we have here. So E is 172 minutes from Y. Okay. Now, if we make the same computation with MR, right? So MR, we'd calculate 76 plus 27. Since this is larger, so that gives us 103. Oops. Okay. Now, since this is larger than the previously recorded distance, right? Because remember, we calculated MR as 96 from Y. But if we go the new route, that's going to be larger than just going MR. So we're not going to record that, or excuse me, we're not going to replace it. So we're going to leave that alone. Okay. So then step 3 and 4, right? We mark P as visited. Okay, so we mark P as visited. And now we designate the vertex with the smallest recorded distance as current. Okay. So we mark P as visited and designate the vertex with the smallest recorded distance as current. So MR and then back to 2. Now, we're now going back to step 2 says for each vertex leading to MR and not leading to a visited vertex. So you notice how here down here P and Y are now canceled, right? So they're grayed out, they're marked. Okay, so notice how MR is not replaced. So we got 172. Okay. And so now we're at MR because MR has the lower of the two, right? 96 and 172, right? We didn't replace this one because it was larger, so we keep that one. So now the smaller of the two is MR. Okay, so now we're at MR. And so we do the same thing. Now we take all of the distances from MR, right? So there's only one, which is A, right? So the distance from A is going to be 79 plus the 96, which gives us 175. Okay, now what do we do from here? Well, follow the algorithm. So steps 3 and 4, we mark MR as visited, and now we designate the vertex with the smallest recorded distance as current. So which one has the smaller recorded vertex? So this is visited. So which one has the smallest recorded vertex? It's going to be NB, right? Because NB is 104, the other ones are 105. So now we go back. Now we're going to start with NB. Okay, so now notice how now here, these are all slashed out, right? They're struck out, right? And now we're doing this one. And now we look at this distance, right? So now A is 140 minutes from our destination. Okay. So again, we just go through the process. And now steps 3 and 4, we mark NB as visited, right? And we choose the smallest distance. So this is visited, so now it's going to be 140 versus 172. Well, 140 is smaller, so that means we're going to be dealing with what? A is going to be now the current. Okay, and then now finally from A, we've got 20. Right? So 20 to 140. So we get T is 160 minutes from Y. Okay? And so what happens now? So now what we do is we mark A as visited, and now we designate E as current because it's the smaller distance of the two between T and E. And then we'd go through it again. Now, the only non-visited vertex leading to E is T. Right? So now we're going to calculate that distance. So T is 160 minutes, 160 minutes. Or hold on a second. Or TA, I'm sorry. For some reason, I was looking at E. But TA, so T, well, hold on a second. E is visited. Right, okay, I'm sorry, I got confused there. So we marked A as visited, right? And then we choose the smaller of the two, which is T. Or excuse me, E, because E is the smallest of the two. Hold on a second. Something's not looking right here. So A is current. T is the only vertex, so we got 160, right? So that was that. Then we mark A as current. Or A is, I'm sorry, we mark A as visited. Right, and then we mark E as current because it's the only non-visited vertex leading to T. Okay, good. Okay, that makes sense. Okay, so now we're on E. So calculating the distance from T to Y going through E is we do 57 plus 172, which gives us 229 minutes. Okay, that makes sense. Okay, good. Now, since this is longer than the existing marked time, we do not replace it, right? So 229 is bigger than 160, so we don't replace it. Okay, now we mark E as visited, and then since all the vertices have now been visited, we're done. So what do we do now? We say from this, we know that the shortest path from Tacoma to Yakima will take what? 160 minutes. And tracking your sequence of edges yielding 160 minutes, that will be the shortest path. So how do we do that? That'll be from here, right? The shortest path is going to be this. Okay? It's going to be along the green line. Now, Dijkstra's algorithm is an optimal algorithm, meaning that it always produces the actual shortest path, not just a path that is pretty short, provided one exists. The algorithm is also efficient, meaning that it can be implemented in a reasonable amount of time. So Dijkstra's algorithm takes around v to the v squared calculations, where v is the number of vertices in a graph. Okay. Now, as we look at the footnote here, it says it can be made to run faster through various optimizations to the implementation of the algorithm. Okay. Now, a graph with 100 vertices will take around 10,000 calculations, but with a computer, that's going to be nothing. Okay. While that would be a lot for us to handle by hand, obviously computers can handle that with no problem. Now, it is because of this efficiency that your car's GPS unit can compute driving directions in only a few seconds. And there's other things about your GPS system that are fascinating too, just from a physics point of view. But that's another discussion. In contrast, an inefficient algorithm might try to list all possible paths, then compute the length of each path, like the brute force algorithm, right? Trying to list all possible paths could easily take 10 to the 25th calculations to compute the shortest path with only 25 vertices. That's a 1 with 25 zeros after it, obviously. Okay. To put that into perspective, the fastest computer in the world would still spend over 1,000 years analyzing all those paths. That's crazy. Absolutely crazy. So definitely Dijkstra's algorithm, much, much more efficient and will always give you the optimal path. All right. Let's do another example here. What do we got here? Yeah, let's do this. Okay, so example 23, it says a shipping company needs to route a package from Washington, D.C. to San Diego, California. To minimize costs, the package will first be sent to their processing center in Baltimore, Maryland, then sent as part of mass shipments between their various processing centers, ending up in their processing center in Bakersfield, California. From there, it will be delivered in a small truck to San Diego. The travel times in hours between their processing centers are shown in the table below. 3 hours has been added to each travel time for processing. Find the shortest path from Baltimore to Bakersfield. So we're going to use Dijkstra's algorithm to figure this out. Okay, so we've got our table. So we've got the different processing centers and the times in between all of the different processing centers. Okay, so we're starting in Baltimore and we want to end in Bakersfield. Okay, so while we could draw a graph, we could also work directly from the table. So here, this is a good example of working from the table. Okay, so we know we're starting in Baltimore, we're ending in Bakersfield. Okay, so the ending vertex is Bakersfield, right? So this is where we're starting. Okay, now we know from Bakersfield we can go to Denver or Dallas. Okay, so we mark Bakersfield as current, and so we look at all the cities connected to Bakersfield. So that's Denver and Dallas. Okay, we've got their distances calculated. So the distances from Bakersfield is 19 and 25. So we're going to first start with Bakersfield, right? So we mark Bakersfield as visited, and now we're going to take the smaller of the two from Dallas and Denver, which is going to be Denver, right? So now, what do? Mark Denver as current in bold. Okay, since it's the shortest distance. Okay, now Bakersfield is grayed out because it's been visited already. We're done. We're not going back there. So now, what do? We look at the distances from Denver, right? Now we're in Denver, and we're going to either Chicago or Atlanta, right? So again, we're going back to step 2. And it says for cities connected to Denver, calculate distances to the end, right? To where? To Bakersfield, right? For example, Chicago is 18 hours from Denver, which means, and Denver's 19 hours from the end. And so the distance from Chicago to the end would be 18 plus 19, which is 37. Okay, so notice here we have in brackets 37, right? Because for Chicago. And then we do the same thing for Atlanta, which is going to be 24 plus 19, which gives us 43. Okay, now what we do is we mark Denver as visited. So notice how it's grayed out. Denver is all grayed out. And now we choose the smaller between Atlanta and Chicago, which is going to be Chicago. And Dallas, or actually, I'm sorry, the other one, Dallas, Chicago, and Atlanta. I'm sorry, of those 3. So now Dallas is the smaller of the 3. Sorry, I missed that one. So now Dallas is the one we're going to go. Now we have 18 and 15. Right? So now what? So let's go back to step 2. And it says for the cities connected to Dallas, calculate the distances to the end. Now for Chicago, the distance from Chicago to Dallas is 18, right? So that's what we have here. Okay? And Dallas is 25 miles from the end. So that means Chicago is going to be what? Or hold on a second. that adds up to what? It adds up to 43. Well, 43 is bigger than 37, so we're not going to replace that. Okay, now we do the same thing for Atlanta. If we add the distance for Atlanta, which is 15 to 25, we get 40. And since 40 is shorter than 43, we're going to replace it. Okay, and so that's now our table looks like this. Now we mark Dallas as visited, right? Now we gray out those. Notice how Atlanta now has 40 instead of 43. Okay, now what do? Now we choose the shorter distance between Chicago and Atlanta, and so we use 37. Okay, so now we're going to use Chicago. And now from Chicago, we've got Baltimore and Atlanta. Okay, so for each one of those, we're going to add. So for Baltimore, we add 37 and 15, which gives us 52. Okay, and so we mark that distance. And then 14 and 37 is 51, which is longer than what we have for Atlanta. So we're not going to replace that. We're going to leave that as 40. Okay, so now we mark Chicago as visited, and this is what we end up with. Now, what do? The distance from Atlanta to Baltimore is 14. So we take 14 plus the 40, which gives us 54. Going to Bakersfield through Atlanta. Now, since this is longer than the currently calculated distance, we do not replace the distance for Baltimore, which is 52. Right, which we got up here. So that means, hold on. So we mark Atlanta as visited, and all the cities have been visited, so we're done. Now, so how do we figure out the shortest distance? The shortest distance is going to be the distance that gives us 52, right? And that will be the route through Chicago and Denver. And how do we, right? So it'll be through Chicago. Yeah, yeah, that's right. Through Chicago, because once you go from Chicago, Baltimore to Chicago is 15. And from Chicago to Denver is 18. And then Denver to Baltimore is 19. And that works. All right. And here we go. Let's do this one. Let's find the shortest path for this one. Okay, so let's take this one step. We're going to go from A to G. So here's our current, right? So the way we're going to do this is we have 6 and 7. Okay, so we're going to mark the 6, right? So this is going to be 6. In brackets. And this is going to be 7 in brackets. Okay, that's a 7, not a 3. Okay, so now the shortest path is going to be here. So we're going to mark G as visited. And now E is going to be the current. Now, with this in mind, so we're going to go B, D, and right? So B, D, and F. So we're at E. Okay, so what do we do? So here, if we look EF, right? If we add from F to E, what do we get? Right? So if we look at F, the distance from F through E to G is going to be 9. Well, the distance from F that we originally have is 6. So 9 is bigger than 6, so we're not going to replace that one. Okay? So now D, what does D get? Okay, D gets marked with what? 6 plus 7, or excuse me, I'm sorry, 2 plus 7, which is 9, so that gets a 9. Okay, and then B, the total is 6 and 7, which is 13. So that gets marked with a 13. Okay, now, so E gets marked as visited. And now we take the smaller of the 3, which is going to be 6. So that's going to be F. So now we look at F as being current. And so we look at the distance between, oh, and we're not visiting E. E's already been visited. So we're not going to do that one. So we're going to go for D and C. So C, let's do D first. So D is 4 from F. So we're going to add 4 and 6 is 10. Now 10 is bigger than 9, so we're not going to replace the 9 for D. We're going to leave that one alone. C is 5 from F, so that's going to get marked with an 11. Oops. Okay, now what do we do? Well, we mark F as visited, and now we take the 3 and we mark, take the smaller of the two. So 9 is the smallest. So D is going to be the current location. So from there, we got B and C. Well, if B is 13, or excuse me, I'm sorry. Where else do we go? Hold on a second. Yeah, so B to D is 3. So if we add 3 to 9, we get 12. Well, 12 is smaller than 13. So we're going to replace the 13 with a 12. And then C through D is 2. So 2 plus 9 is 11. So that's the same as what we have for C. So we're not going to replace that. Okay, we're going to leave that alone. So now D gets marked as visited. And now we take the smaller of the two vertices between D and C. And since C is smaller, we're going to take C, make C current. And the only non-visited vertex is A. So if we take 4 plus 11, that gives us 15. Okay. And then now we mark C as visited, and now we take B as current because it's smaller. And the only vertex that we haven't visited is A, right? So A to B is 1. So we add 1 to 12, which is 13. Now 13 is smaller than 15. Oops. No, come on. And so we're going to, this is going to be 13. Okay, so we replace the 15 with the 13. And so now B is marked as visited, and we're done. So now what happens? Well, the shortest route is going to be through B. Okay, so it's going to be A, B, right? So it's going to be A, I'll draw it out. So A to B, and then B to D, right? And then C, or D to E, and then E to G, right? And so that gives us the 13. 7, 8, 9, 10, 11, 12, 13. So this is the shortest route, or the shortest path from A to G. All right, and that completes chapter 1 and our discussion on graph theory.